Welcome to the deep dive. Today, we're embarking on a pretty serious mission. Think of it as cosmic archaeology.
Yeah, but instead of digging for old bones, we're searching the skies.
Exactly. We're looking for the oldest, faintest relics in the entire universe. Astronomers have this great name for them: stellar ghost towns.
Ghost towns. And finding them isn't just, ticking a box. It's actually central to understanding a huge moment in cosmic history.
Right. These relics, they might just be the missing piece we need to solve one of the biggest puzzles since the Big Bang itself.
We're talking about the epoch of reionization, that instant when the entire universe kind of flipped a switch and lit up for good.
Okay, but here's the challenge, and it's a big one for you, the listener, to grasp. How on earth do you find a galaxy that's tiny, incredibly far away, maybe even hidden by dust?
And so faint, it barely registers. I mean, it's practically invisible noise. These ultra-faint dwarf galaxies, or UFDGs, yeah, finding them with standard telescopes is almost impossible.
So if our telescopes on Earth aren't quite cutting it, what do we do?
Well, we get clever. We stop trying to just build bigger lenses here and start using the universe itself as a giant magnifying glass.
Ah, nature's telescope.
Exactly. Strong gravitational lensing. That's the focus of our deep dive today. We're going to explore how this natural lensing effect lets us see these cosmic ghost towns.
And how that, in turn, gave us the evidence for what really powered that cosmic dawn, right?
Precisely. We've got some fascinating sources lined up, some recent discoveries like the Sculptor A, B, and C galaxies.
Oh, yeah, those isolated ones. Yeah.
And data from huge projects like the Hubble Frontier Fields. It's quite a story.
Okay, let's dive in. All right, so first things first, let's properly define our targets, these UFDGs. What makes them a ghost town specifically, not just, a small galaxy?
It's about scale and, well, life, or lack thereof, compared to our Milky Way. Hundreds of billions of stars, right?
Yeah.
But these things have maybe a few hundred to a few thousand stars total.
No, okay, that's
Incredibly tiny. They're the smallest type of galaxy we know. But the ghost town part comes from the fact that they're dead permanently. They only contain really, really old stars. And crucially, they're completely empty of gas.
Ah, the gas. Stuff you need to make new stars.
Exactly. No gas, no star formation. So they formed some stars way back in the early universe, and then nothing. Just fading embers, ghost towns.
Now, for a long time, we thought we knew why they lost their gas, didn't we? The common idea was they just got too close to a big galaxy like ours.
Right, the neighborhood bully theory.
Yeah.
A massive galaxy like the Milky Way or Andromeda would gravitationally strip the gas away. Tidal forces.
Yeah.
That's been the standard explanation for decades.
But then came these sculptor galaxies, A, B, and C. Tell us about those.
Yeah, this was a key discovery. Astronomers found these 3 UFDGs near a galaxy called NGC 300, which is about 6.5 million light years away. But the crucial thing is they're isolated. They're nowhere near a massive gravitational bully.
So whatever stripped their gas, it couldn't have been a giant neighbor?
Exactly. That observation really forced us to reconsider. If it wasn't external stripping, it had to be something internal or something universal happening very early on.
Okay, so this narrows it down. What are the main suspects now for why these tiny galaxies became ghost towns so early?
Well, there are 2 leading theories now. The first one is purely internal. Supernovae.
Explosions from within.
Yeah. Think about the very first stars that formed in these tiny galaxies. They're likely massive, lived fast, and died young in incredibly violent supernova explosions.
Okay.
Now, these galaxies are so small, their gravity is really weak, a shallow gravitational well, we say. So these massive explosions throwing out material at like tens of millions of miles per hour.
That could just blow all the remaining gas right out of the galaxy.
Potentially, yeah. Just clear it out completely, leaving it sterile, unable to form any more stars. That's one possibility.
But there's another suspect, right? One that ties into that bigger cosmic event you mentioned.
The prime suspect, really, is the epoch of reionization itself.
Yeah.
That period shortly after the Big Bang when the universe transitioned.
From dark and foggy to clear and bright.
Pretty much. It went from being filled with neutral hydrogen gas, which is like a thick fog, to UV light, to being transparent, ionized. And that transition was driven by a massive flood of high-energy, ultraviolet photons across the cosmos.
And those photons, they could have affected these tiny galaxies.
Oh, absolutely. Imagine UV light so intense, bathing these little fragile galaxies, it could have literally boiled away or ionized and dispersed the gas within them.
So the ghost towns are like casualties of the universe turning on its lights.
That's a great way to put it. There are cosmic evidence of this massive event. And here's the kicker. If we can figure out how many of these tiny galaxies there were back then, it helps us understand what caused reionization in the first place.
Okay, so we have these crucial targets, the UFDGs, the ghost towns, but they're basically invisible. How do we actually see them? This brings us to strong gravitational lensing, SGL.
Right. And this is where things get really cool, honestly. It's a direct prediction of Einstein's general relativity in action.
So how does it work, in simple terms?
Basically, you need a really massive object sitting in the foreground. Usually it's a huge galaxy cluster, thousands of galaxies, tons of dark matter, immense gravity.
Okay, a cosmic heavyweight.
Exactly. And its gravity is so strong that it actually warps space-time around it. So light from an object far, far behind this cluster doesn't travel in a straight line anymore.
It gets bent.
It gets bent, yeah.
Yeah.
And focused, kind of like a lens. The cluster acts as a natural telescope, magnifying the light from the distant background source.
And we call it strong lensing when the magnification is significant.
Yeah. Typically, the definition is a magnification greater than 2 times. But often, it can be much, much higher, 10, 20, even 50 times or more.
Wow. And this creates some pretty weird visuals, doesn't it? I've seen those Hubble pictures.
Well, they're spectacular. You get these stretched out arcs of light, sometimes smeared into almost perfect circles. Those are called Einstein rings.
Einstein rings, right.
Or sometimes the light gets split, and you see multiple images of the exact same distant galaxy jotted around the foreground cluster. An Einstein cross is a classic example.
But hang on, if the image is so warped and distorted, isn't it like looking through, I don't know, the bottom of a glass bottle? How do you know what the original galaxy actually looks like?
That's a really good question. It is like a funhouse mirror. Absolutely.
Yeah.
But the key is we can model the mirror. We can map the mass distribution, the foreground cluster of the lens pretty accurately.
How?
By looking at how it distorts all the background galaxies, by measuring the positions and brightness of the multiple images, and using our understanding of gravity.
Right.
Once you have a good model of the lens.
You can mathematically undistort the image.
Exactly. You can correct for the lensing effect and reconstruct the true size, shape, and brightness of the distant source galaxy. It's computationally intensive, but it works.
And this is what projects like the Hubble Frontier Fields did.
Precisely. They stared deeply at several massive galaxy clusters, using them as natural lenses. And the results were revolutionary because it pushed the detection limit way, way down.
How far down? You mentioned 10 to 50 times fainter.
Yeah, intrinsically fainter, meaning we could suddenly see galaxies that were, in reality, 10 to 50 times dimmer than anything Hubble could have possibly seen directly. It opened up this whole new population of incredibly faint objects in the early universe, like finding micro-villages where we could only see cities before.
That's amazing. And it's not just about faintness, is it? You mentioned dust earlier. Does lensing help with dusty galaxies too?
It does. It plays double duty. There's a whole class of galaxies called dusty star-forming galaxies, or DSFGs. They're often quite massive and forming stars like crazy, but they're so shrouded in dust that they're almost invisible in optical light, like what Hubble sees.
So how does lensing help find them?
Well, you combine the lensing effect with observations at wavelengths that can penetrate dust, like sub-millimeter waves from telescopes like JCMT. Researchers looked at known dusty sources in lensing fields.
And checked if their apparent brightness was boosted by the lens.
Right, and they found that, yeah, about 1% of the dusty galaxies they studied in a certain brightness range were actually being significantly amplified by a foreground lens. So lensing helps us uncover anything that's faint or hidden, whether by distance or by dust.
And we can even figure out their properties. You mentioned an example, SPT something.
Ah, yes, SPP0615JD. Fantastic case study. This was an extremely distant galaxy seen only about 500 million years after the Big Bang. Tiny. It appeared as this highly magnified, stretched out arc thanks to a foreground cluster.
And by analyzing that arc.
By analyzing the arc and modeling the lens, scientists could figure out its actual intrinsic properties. Turns out, it was incredibly small, less than 2,500 light years across, and had a very low mass, under 3 billion solar masses. A true galactic embryo, magnified for us by cosmic chance.
Okay, this lensing technique is clearly powerful. Let's bring it back to the big mystery. The epoch of reionization, that cosmic fog clearing.
Right. The central question was always, what provided the sheer amount of ionizing UV energy needed to do that? To ionize nearly all the hydrogen in the entire universe.
Was it a few really bright, massive galaxies, the cosmic supercities? Or was it something else?
Or was it the cumulative effect of billions and billions of much smaller, fainter galaxies, those microvillages, the UFTGs we've been talking about. To answer that, you absolutely have to be able to count the faint ones. You need a proper census.
And that's where strong gravitational lensing becomes the essential tool.
It's the critical enabler. Because it magnifies these incredibly faint galaxies, it allows us to count them accurately at much dimmer levels than previously possible. This lets scientists measure what's called the ultraviolet luminosity function, or UVLF, especially its faint end.
The UV luminosity function. Okay, that sounds technical. What does it actually tell us?
It's basically a cosmic population count, sorted by brightness. It tells you how many galaxies there are at each level of UV brightness, or luminosity. The faint end refers to the part of the count that deals with the dimmest galaxies.
So what did the lensing-assisted census reveal about that faint end in the early universe?
It revealed the smoking gun. The measurement showed that the faint end slope of the UVLF at high redshift around the time of reionization is incredibly steep. Something like alpha equals -2.
Okay, steep slope, -2. Translate that for us.
Yeah. It basically means that faint galaxies wildly outnumbered bright galaxies. For every one big, bright galaxy, there were hundreds, maybe even thousands, of these tiny, dim ones. The universe wasn't dominated by a few lighthouses. It was absolutely saturated with faint little light bulbs.
Wow. So the sheer number of them was overwhelming.
Totally overwhelming. That steep slope confirms that these faint galaxies were by far the dominant population in the early cosmos.
So even though each one wasn't putting out much light individually,
when you add up the UV light from all of them, billions upon billions, the total amount of energy is staggering. This is the power of the small.
And that total energy budget, was it enough?
Yeah.
Enough to reionize the universe?
That's what the calculations showed. When scientists integrated the UV luminosity function, considering this huge population of faint galaxies revealed by lensing, they found the total UV luminosity density was massive.
Enough on its own.
Almost. It was mathematically sufficient to keep the universe ionized if, and this is an important point, a reasonable fraction of that UV light could actually escape the galaxies.
Escape? What do you mean?
Well, a lot of UV light produced by young stars gets absorbed by gas and dust within the host galaxy itself. It never makes it out into the intergalactic medium where it's needed for reionization. So we need an escape fraction, or $5.
Okay, so what escape fraction do we need from these faint galaxies?
The calculation showed you only needed an escape fraction of about 10% to 15%, meaning if just 10–15% of the UV photons produced inside these countless faint galaxies managed to leak out, their combined light would be enough to do the job.
And is 10–15% considered plausible?
Yes, very plausible, especially for these small, low-mass galaxies which might have less gas and dust to block the light, or more turbulent structures due to feedback from stars and supernovae, which could create escape channels.
So the conclusion is pretty solid then.
The observational evidence, significantly boosted by lensing, points squarely at this solution. It wasn't the few bright giants, but the collective power, the sheer overwhelming number of tiny, dim star systems, including those ancestors of today's ghost towns, that drove the cosmic dawn. They turned the lights on. And, getting this precision relies on some clever techniques even before lensing comes into play, just to find these potential high redshift candidates.
Ah, right. You have to identify things that are incredibly far away first. How's that typically done?
The workhorse method is called the Lyman break technique, or sometimes the dropout technique.
Dropout? Sounds like they're failing a class.
Huh? Sort of. It relies on hydrogen. Neutral hydrogen gas is really good at absorbing UV light, specifically light bluer than the Lyman alpha wavelength. Now, for very distant galaxies, the universe's expansion stretches out, the light redshifts it. So that sharp absorption edge, the Lyman break, gets shifted way down into the visible or even infrared part of the spectrum.
Ah, I see. So you look at the galaxy through different color filters.
Exactly. You use broadband filters, and if a galaxy is extremely distant, it will appear bright in, say, an infrared filter, but suddenly become very faint or completely invisible. It drops out in the next bluer filter because its Lyman break has been redshifted past that filter's wavelength.
So the color pattern or lack thereof tells you its approximate distance.
Precisely. By seeing which filter it drops out of, you can get a good estimate of its redshift, its distance. That's how astronomers build catalogs of high redshift candidates to then study further, perhaps looking for lensing magnification.
Clever. And looking ahead, this whole field, finding lensed galaxies, studying the faint population, it's not slowing down, is it?
Oh, not at all.
Yeah.
It's actually poised to accelerate dramatically. We have amazing new tools coming online or already delivering.
Like the James Webb Space Telescope.
JWST is a game changer, absolutely. Its sensitivity and resolution, especially in the infrared where the light from these distant objects ends up, is perfect for this. Plus, upcoming survey telescopes like Euclid and the Roman Space Telescope are designed to scan huge areas of the sky.
So they'll find many more strong lensing systems, more foreground clusters acting as telescopes.
Exactly. They'll significantly increase the number of known lenses, which means we'll find vastly more lensed background galaxies, including these faint ones from the epoch of reionization.
And what will that extra data allow us to do? We've sort of solved the basic who-did-it mystery for reionization, right?
We have a good handle on the faint galaxies. But the next big question is how it happened in detail. Was reionization a smooth, uniform process across the whole universe simultaneously? Or was it patchy? Did it happen in bubbles, perhaps starting around the most clustered regions of these faint galaxies, which then grew and merged until the whole universe was clear?
Mapping the process itself.
Exactly. With much larger samples of these early galaxies, thanks to new telescopes and more lensing discoveries, we can start to map out the spatial distribution and timing of reionization in much finer detail. That's the next frontier. #outro.
It really is an incredible story when you step back. We had this fundamental mystery about the universe's dawn, these almost invisible ghost town galaxies holding the clue.
And the universe itself provided the tool needed to see them using the gravity of massive structures as a lens.
We use the biggest things we know, galaxy clusters, to study the absolute smallest things, these UFDGs. It's quite poetic in a cosmic way.
It really highlights how interconnected everything is in cosmology. Studying the large scale tells you about the small scale, and vice versa.
So the final thought we want to leave you, the listener, with is this. If using gravity, the warping of space-time by massive objects proved to be such a powerful tool for observing the faint and distant universe.
If the most effective way to study the grandest structures like galaxy clusters and dark matter is through their subtle lensing effects on the tiniest, most fragile background galaxies,
then what other fundamental laws or properties of the universe might be out there waiting to be discovered that could turn the cosmos into an even more powerful observational instrument for us in the future?
What else is nature hiding that could become our next cosmic telescope? The search, as always, continues.
Join us next time on The Deep Dive.